We are still on heat capacity and specific heat capacity. Now, we are looking at methods of determining heat capacity, and in the morning we went as far as electrical method, and we looked at how we can determine the specific heat capacity of solids using the electrical method. Now, we want to go to fluids. And probably find out what is the difference between the specific heat capacity of a liquid and that of a fluid. Now, when we were looking at the solids, we were able to discover that you determine the specific heat capacity by equating the heat that is obtained from the heater coil. You equate it to the heat absorbed, or what we call the heat gained, which is given by mass multiplied by specific heat capacity of the solid and the subsequent change in temperature. Now here, we took the heat that was supplied to be going direct to our solid. But in our case, we discover that a liquid cannot exist on its own. It has to be put in a container. Therefore, now when we are determining the specific heat capacity, what we should have in mind is that the heat that has been supplied by our electrical apparatus is supposed to go into our liquid as well as the container. Therefore, heat that has been supplied is going to be equal to heat absorbed by liquid added to heat absorbed by the container. So here we are adding a concept of the container. Let us take an example to that effect. Now the question reads, in an experiment to determine the specific heat capacity of water, an electrical heater was used and the voltage supplied was 24 volts and the current was 2.0 amperes. Now, we are required to get the specific heat capacity of water if 1.5 kgs of water in a 0.4 kgs calorimeter had its temperature rise by 6 degrees centigrade, and the time is given as 13.5 minutes. Now let us look at the information that we have. Now we have the mass of water given as 1.5 kgs. Now mass of the calorimeter is 0.4 kgs. Again, we have the time as 13.5 minutes. This one we change to seconds. Change to seconds. We get 810 seconds. Then we have the voltage being equal to 24. Current is 2.0 amperes. Now we are supposed to calculate the specific heat capacity of water using the information. Now here we equate the heat supplied by the heater. We equate this to heat gained by water plus the heat gained by the calorimeter. Heat gained by water and the heat gained by the calorimeter. Now, for all of them, temperature rose by 6 degrees centigrade. That one is very important. The temperature of the two rose by 6 degrees centigrade. Now, on this side, the heat supplied, which is equal to the work done by the electrical energy, is going to be given by mass of water. This one we multiply by the specific heat capacity of water and the change in temperature of water plus heat gained by the calorimeter given by the product of the mass of the calorimeter, specific heat capacity of the same, and the change in temperature of the same. Now, let us substitute what we have into our equation. On my left-hand side, I have voltage as 24, current as 2.0, time as 810 seconds. No. This one will be equal to the mass of water, which is 1.5 kgs. This one we multiply by specific heat capacity of water, which we are looking for. Then, and the change in temperature, which is 6. This one we add to mass of the calorimeter, which is 0.4. We multiply by its specific heat capacity, which was given as 400, and then the change in temperature, which was 6. Now let us simplify that equation so that on the left hand side we have 38,880 being equal to 9 CW. When we add that one to 960 joules. But we are still looking for the specific heat capacity, so let us collect the like terms. We subtract 960 both sides to be left with 9 multiplied by our specific heat capacity of water, and that is 7,920 joules is equal to 9 times specific heat capacity. Now we can divide throughout by 9 so that we obtain our specific heat capacity as 4,213 joules per kilogram Kelvin. 4,213 joules per kilograms Kelvin. Now, we can now look at our next method. We can look at our next method, which we are going to call continuous flow method. Continuous flow method. And basically, continuous flow as a method of determining the specific heat capacity is used with fluids. Whereby we mix fluids at different temperatures for us to obtain the desirable degree of hotness. Here, mainly the method is used with fluids, and by fluids we mean liquids and gases. Liquids and gases, and it involves mixing fluids at different temperatures to obtain the desirable degree of hotness. That we cannot use this method with solids, but rather we now narrow down to fluids, which are liquids and gases, and we mix fluids at different temperatures so that we can obtain a desirable degree of hotness. Let us take an example or two. Let us take an example or two. Now, the question reads that a person wanted to have a warm bath of 40 degrees centigrade, and he placed 5 kilograms of water at 85 degrees centigrade in a basin. Now, we are required to determine the mass of water at 25 degrees centigrade that should be mixed with his water so that we can obtain the desired bath. Now, from the question, we have been given the initial mass of water as 5 kgs. Now, the first water, change of temperature, which we are calling delta theta, should be from 85 to 40 degrees, which gives us a change of 45 degrees centigrade. Then the final water, or the other bit of water, should say that mass of water initially was 5 kgs. Now the temperature will change by 45 degrees centigrade. That is the first 5 kgs of water. The second mass of water which you are supposed to determine should have its temperature change from 25 to 40. So it should change by 15 degrees centigrade. Then we have the specific heat capacity of water being given as 4200 joules per kilogram Kelvin. Now, here we have 5 kgs of water changing its temperature from 85 degrees centigrade to the desired 40. So that means we should mix it with some other water at a slightly lower temperature, so that now some heat is lost by our 5 kgs of water, and the same heat is supposed to be gained by the final amount of water. Now, let us get that mass. Let us get that mass of water that we require. Now, what we will realize is that heat lost by 5 kgs of water should be equal to the heat gained by water of mass m. The water, we are calling it mass m because we do not know the mass that we require to be in a position to mix with our first bit of water to achieve the desirable 40 degrees Celsius. So in this case, the heat lost will be given by mass of water multiplied by the change in temperature of the same multiplied by the specific heat capacity of water, and that one is going to be equal to the mass which we are looking for. We multiply by the change in temperature and the specific heat capacity of the same. Now, let us substitute in our equation. We put in the values that we have so that now we can work from the known to the unknown. The mass of our water in the basin initially was 5 kgs. Now, it is supposed to change its temperature by 45 degrees Celsius, and its specific heat capacity is 4200 joules per kilograms Kelvin. This one we can equate it to the mass which we are looking for. We multiply again by the specific heat capacity of the same, and we multiply by the change in temperature, which is 15 degrees Celsius. 15 degrees Celsius. And now here we can cancel the specific heat capacities. We can also cancel by 15 3, so that now our 5 times 3 is now 15 kgs, which is the mass we were looking for. Therefore, even though you are mixing the same liquid, you are supposed to realize that the heat lost by your initial liquid will be the same heat that will be absorbed by the second bit of the liquid with which you mix the first one. Let us look at another example. Let us look at another example. The question reads, a person needs water for use at 50 degrees centigrade. Find how much water at 80 degrees centigrade should be added to 60 kgs of water at 10 degrees centigrade to achieve the desired temperature. Again, let us look at what we have from the equation. From the equation, we have been given a mass of water to be 60 kgs. Temperature change will be from 10 to 50. That means 50 minus 10, so we can obtain 40 degrees centigrade. The specific heat capacity of water is 4200 joules per kilograms Kelvin. Now, this one, we are now required to get the mass of water at 80 degrees centigrade that should be used. So here our delta theta is going to be from 80 to 50, so 30 degrees centigrade, and then the specific heat capacity is 4200 joules per kilogram Kelvin. Joules per kilogram Kelvin. Now, we realize from this question that we have our first amount of water is going to gain heat. That means that heat is supposed to come from the second amount of water, which we do not know how much it is, but again, it is supposed to be equal. The heat gained and heat lost should be equal. So let us use that concept to come up with the mass of water that we require to add. Now here we say that heat lost will be equal to the heat gained. Heat lost is actually equal to the heat gained. Now in this case, the heat lost will be the mass that we don't know. We multiply that by 30 degrees centigrade, and then we multiply by our specific heat capacity. This one is going to be equal to what is gained by 60 kgs of water. Its temperature rises by 40 degrees centigrade, and its specific heat capacity is 4200 joules per kilograms Kelvin. Now, we are supposed to cancel out so that we can be left with the mass. And our mass is finally going to be 40 kgs. 40 kgs. So by equating the heat gained to the heat lost, we can be able to achieve the mass or any other parameter that we seek to calculate as far as we insert the correct figures into our equation. As long as we insert the correct figures into our equation. Now, this method in itself, the continuous flow method, has some advantages over the other methods of determining heat capacity. And the number one is that it can be used to determine specific heat capacity of gases, specific heat capacity of gases. That is one of the advantages. Number two is that we do not consider a container in our calculations. Those are then number three is that now from the other methods that we have looked at, you realize that there is no other method that took care of gases. Yet gases also have specific heat capacities. So we need to find a way of determining specific heat capacity of gases as well. This method provides for the same. Again, we also need to minimize our chances of making mistakes. And in our case, we are only interested in the fluid and not the containers in which the fluids are put. That means we have minimized our chances of making mistakes a great deal. Number three is that no losses of heat to the environment as conduction and convection are minimized. By the presence of a vacuum. That conduction and convection are taken care of by the presence of a vacuum. Also, most importantly is that small range of temperature can be accommodated. Small temperature range can be accommodated by our method. Those basically are the four main advantages of this method over the other methods. Those are the main advantages of this method over the other methods. Now, too much about methods of determining specific heat capacity. We need now to revisit our introductory bit. We agreed that if heat is lost or absorbed, there are some changes that we are going to realize or some effects that are going to come about as a result of the same. Now, number one, we said there could be change in temperature. Change in temperatures. Number two is that work could be done And number 3 is that you can achieve change of state. You can achieve change of state. Now, for the change in temperature, we have really expounded on that, and we have used change in temperature to calculate different parameters of our interest. Now, the work done, we have already been able to accommodate it in the electrical method, where we have said that the work done is the same as the heat energy that has been absorbed. Now, we come to the last aspect, which is the change of state, and find out how does heat affect change of state. Now, maybe we can revisit the issue of the states of matter, and we say that matter exists in the 3 states where we have solids, we have liquids, and we have gases. Now, again, we say that depending on whether the heat we are talking about is being absorbed or lost, we could achieve change of state to or from any state of matter as follows. You could have a solid, here you could have a liquid, and again you could have a gas. Now, a solid can change into a gas through a process we are going to call A. Now, a liquid can change to a gas through a process we could call B. And now, the reverse could also happen, where now we could have process C changing a gas to a liquid, and process D changing a liquid to a solid. We could also have another process that would take a liquid direct to a gas, and this process I want us to call it E. And then we have another one we are going to call F, which is the change from gas direct into a solid. Now, I want us to name those processes. Where process A, we call it melting. Process A is what we call melting. Process B is what we call vaporization. Process C, we call it condensation. D, is solidification. E is sublimation, and F is also sublimation. Or you could also call it decomposition. Some literatures will call it decomposition. Now, based on whether heat is absorbed or released, we have 6 basic processes that could take place in as far as states of matter is concerned. Now, let us look at the processes on my left hand side. These ones. Process A, B, C. We could also add D. We could also add D here. We could also add D, which is sublimation. Sublimation. Now, these four processes involves absorption of heat. These others involves loss of heat. That process A, B, C, and D, A, B, C, and D involves change of state through absorption of heat. Now, when heat is lost, we could also achieve process now this one is E. This one is E. D is what we call A, B, E. This is F actually. Sublimation. Then we have D. We call it, let's see, we call it condensation. We have D is solidification. F, we call it sublimation or decomposition. Now, we have named our processes. Process A, change of state from solid to liquid, is what we call melting. B is from liquid to gas. That one we call it vaporization. We can have E, where our solid changes direct into a gas without passing through the intermediate liquid state. We call it sublimation. Then we have process C, which we call condensation. D is solidification, and we could also have F, which is called decomposition. Now, looking at our diagram, process A, B, and E. Processes A, B, and E involve heat gain, while process C, D, and F involves heat loss. Heat loss. Now, one interesting thing we are going to discover when there is actually change of state, you continue heating or cooling until a process, one of these processes is complete. You will realize that when the change of state is taking place, temperature does not change. That when change of state is taking place, when change of state is taking place, temperature does not change. When change of state is occurring, you realize that temperature does not change. Now the question is, does it mean that even though we continue heating, no amount of energy is absorbed? That even if we continue cooling, no amount of heat is being lost? No. There is energy that is involved in the change of state, and that energy absorbed to change state is used to break forces between particles of matter. That though there is no rise or drop in temperature, what we are using the energy to do once the energy is absorbed is to actually break forces between particles of matter. Now remember that matter is made up of particles, and therefore there are those forces that hold particles together. Now, if you want to break the particles so that probably you can increase the vigor with which particles move and achieve a change of state, you have to take care of the forces, and the process will involve breaking the forces between particles, and that of course is going to need some energy. Now, how about when you are losing energy? Now, we have seen that you can also achieve a change of state by losing energy. Now, the energy lost when change of state occurs is used to form bonds or to strengthen the forces between particles. Now, we are realizing that you can make or break a force, and in both cases energy is involved. Only that now when you want to make a force, you have to lose energy, and at the same time when you want to break a force, you have to supply energy. Now that is exactly why we say there is no change of temperature, because the energy basically is supposed to make or break the forces between particles. Now, this energy absorbed or lost to achieve change in state or change of state without rise or fall of temperature is called latent heat. This is what we call latent heat. Now we have already realized that there is that energy that we need to lose or even gain to make or break forces between particles of states of matter, and that energy is going to be absorbed or lost without change of temperature, and that energy is what we call latent heat. Now we have two types of latent heat. We have two types of latent heat. We have what we call latent heat of fusion, and we have latent heat of vaporization. Those are the two types of latent heat that we have. One is latent heat of fusion. Again, we have latent heat of vaporization. Let us look at each one of them at a time, and we begin with latent heat of fusion. And latent heat of fusion in itself being a form of energy, we define it as the energy required, or we can say absorbed, to change a given mass of solid to liquid without change in temperature. That there will be some energy that will be required to change a given mass, Not that we are not specific. We are working with the mass that we have been given. That energy we require so that we can change a solid to a liquid without that change in temperature is what we call latent heat of fusion. Here, it is going to be used in the process of melting. So when melting is occurring, latent heat of fusion is absorbed. Or fusion is actually absorbed. Now, when we want to freeze, the process of freezing, now this one involves giving out latent heat of fusion is actually given out. So there are two processes that will involve latent heat of fusion. Now, because we said that latent heat could be absorbed or even given out depending on what you want to achieve. Now, follow our definition. We have just used a solid to a liquid, but we do not limit ourselves to that. You could also give it out for you to change a liquid to a solid. That one is also a valid definition. And now, that brings us to the two processes that will need latent heat, where melting will involve absorbing in order for us to break the forces between particles. And again, freezing will involve giving out of latent heat of fusion for you to achieve that desired change of state from a liquid to a solid. Now, let us define latent heat of vaporization. But before then, we could draw what we call a heating curve, where we have let us take an example of ice. Now, this being the temperature, that being the temperature, and this is time S. Now, let us imagine that we are heating ice, a given mass of ice from -10 degrees centigrade. We can call it -5 degrees centigrade. This is 5, this is 10. Now, you realize that we are going to have rise in temperature. With time, temperature is going to rise. Up to a given point. At 0 degrees centigrade, that is where we achieve the change of state from solid and to liquid. And we said we are going to supply some energy without realizing change in temperature, beyond which now temperature will increase again with time. So here we have temperature increasing. Here we have change of state. And again, after we have achieved our change of state, now temperature rises again. Temperature rises again. Now, that means to achieve the change of state here, we are supplying energy, but we have no change in temperature. Now, the type of energy that is absorbed at that point is what we call latent heat of fusion. Latent heat of fusion. Now, next time we meet, we are going to discuss how we can incorporate this concept of latent heat of fusion in our calculations and find out how it affects heat as a form of energy. Thank you.